And then I'm going to share my screen so we can kind of get on the same page. Okay, so today is Monday, April the 10th, and I do have the midterm exams graded. So you should be able to go in and view your score and then look at what you missed. And if you have questions, I'm more than happy to try to answer those for you. Project 2 was due last night, which was Sunday, April the 9th. I can tell that several of you submitted those. I haven't had the opportunity to grade those yet, so I'll be looking over those later today or tomorrow. Just a heads up, mini project number 3, which will be related to the test for normality, is due on Sunday, April the 16th. The topics that we're going to get into today are hypothesis testing. We're going to talk about the difference between parametric and non-parametric test, and then also look at the test. It's only one, I've got it plural. The test for normality. It's not plural, it's just one. But I want to point out a couple of things in D2L. So let me go over to the course. Couple of things. One is actually on Saturday, I posted a set of fill in the blank notes. The topic of hypothesis testing is going to be the topic of discussion really from now until the end of the term. We talk about a variety of hypothesis tests throughout Module 3 and Module 4. So it is a very important topic. It is one of the key procedures or key processes that you learn in this course. And so it's a very it's a step-by-step process, and the steps do not change. And so I have that set of fill in the blank notes. You can print them off and fill them in as we go, or if you want to try to have your computer opened up and fill them in, that way you can also do that, but I've made that available. I want to look at, I don't normally, but I do want to look at the introduction to Module 3, because we're going to begin to move from kind of learning how to describe the data set into more of making inferences. Remember, we talked early on at the beginning of the term that there are two branches of statistics. You have descriptive statistics, where you describe the data. That's basically stating just the facts, the mean, the median, the mode, the range, the number of values you have. You're stating facts about the data set. As we move into Module 3, we're going to move into the branch of statistics called inferential statistics, where we actually begin to use the data, use those descriptive statistics to interpret the data, and maybe even inserting some of our own perspective, our own interpretation, to make generalizations about our population parameter. And one of the big buzz phrases that you hear now, especially in the business world, or really in any kind of industry, is they want to make data-driven decisions. And so that's kind of the focus we're going to have, because statistics can help you make decisions, or at least support the decision that you make. And so researchers and statisticians are maybe asked to provide information about a variety of population parameters. The example that I give here is Georgia's public broadcasting system, PBS, may want to know how many Georgians watch their programs each week. But it's impossible, and we've talked about how it would be impossible to survey each and every household that watches PBS, or each and every household in the state of Georgia, because it would be expensive, it would be time consuming, and we probably still wouldn't get every household. So, but PBS needs the information the best information possible, so they can make decisions. And so that's where inferential comes into play. Inferential statistics comes into play, because we can take what we learn about our small group, our sample, and we can infer it, make a generalized statement to apply it back to the entire population, or in this case, to the state of Georgia. And the process that is used to do that oftentimes is called hypothesis testing. With hypothesis testing, the idea is you want to determine if your proposed answer to the question is valid or invalid. Is it a good decision, or is it a bad decision? Are you on target, or are you not on target? And so we're going to be focusing on how to do a hypothesis test throughout the rest of the semester, because we're going to look at a wide variety of hypothesis tests. Okay? So again, just to remind you, in case you came in after I mentioned it, I did post on Saturday the fill-in-the-blank notes that we're going to use this morning in our discussion. Okay? So I'm going over to my fill-in-the-blank notes. If you'll recall, we noted that all research, statistical research, scientific research, all kinds of research, begin with a question. And so we pose that question clearly and with as much detail as possible, so that ultimately we can identify the variable, the population, the parameter, the sample, and the statistics. And we talked about that early on in the course. But one of the intermediate steps that we really didn't talk about is oftentimes when you pose that question, you also have, maybe in the back of your mind, in your gut, you have an idea of what you think the answer should be. And in statistics, that's what we call the hypothesis test, or the hypothesis. You're familiar with science. In science, we use that phrase hypothesis, and it usually means an educated guess. It still kind of means that in terms of statistics, but we often think about it more so as the proposed answer to the research question. Now, again, if we were in a laboratory, like in a chemistry class or a biology class, we would propose our hypothesis, and then we would perform the experiment to see what happened, and did it meet our expectations? Did what we think should, could, would happen really happened. And it's the same idea with hypothesis testing in statistics. We want to determine if our proposed answer to the research question was good. Did we make the right decision? Or is our proposed answer a good one or a bad one? And it's a very lockstep process, if you will. These same steps that we're about to outline are the same every time you do a hypothesis test. What changes is what type of test do we perform. I hope if you've had Statistics 1401 or Elementary Statistics 1 recently, this should sound familiar. If it's been a while, hopefully you can pick back up on it very quickly. So we're going to begin, and the first step in the hypothesis testing process is to state the two opposing hypotheses. You technically always have two hypotheses. You kind of have like a good one and a bad one, the pro and the con. Okay. The first hypothesis is called the null hypothesis. The symbol we use a capital H with a subscript of 0. You may not be aware, but the word null is kind of an old English word that actually means 0. So we have the capital H for hypothesis and a subscript of 0. And it is a claim about a population parameter that is assumed to be true throughout the entire process. It must always contain equal in some form. You can almost think about hypothesis testing like a court case. Within the United States, a defendant is presumed innocent until proven guilty. And so in this process of hypothesis testing, the null hypothesis is assumed to be true, to be accurate, to be valid until we prove otherwise. The phrase that tends to bother students is that phrase that it must always contain equal in some form. When you're stating the null hypothesis, you could say that it is equal. It could be less than or equal, or greater than or equal. Those are your three options. The phrasing in the scenario, or the phrasing of your self-identified hypothesis, is going to determine which one of those symbols you're going to have. Is it going to be just equal? Could it be less than or equal? Could it be greater than or equal? And we'll be looking at how to make that decision. The second hypothesis is called the alternative. The symbol for the alternative hypothesis is the capital H, again for hypothesis, and we have a subscript of A. It is a claim about the same population parameter that is the exact opposite of the null, which means it will never, ever contain equal in any form. So if we're thinking about the symbols that could be in our alternative hypothesis, they have to be the exact opposite. So the exact opposite of equal would be not equal. The exact opposite of less than or equal is greater than. And the exact opposite of greater than or equal is less than. Guys, they're always paired this way. If the null is equal, the alternative has to be not equal. If the alternative is less than, then the null has to be greater than or equal to. They're always paired together in this form, in this way. One of your hypotheses will be given to you in the scenario. The challenge that we have is identifying which one we have. And it will all be based on the phrasing and the words in the problem. The alternative hypothesis tells us some other things. It also tells us kind of what type of test we have, what type of test. And the type of test is important because you do have to identify that when you're doing it, either if you're doing calculations by hand, if you're doing calculations in Minitab, if you're doing calculations on your calculator, if you're doing calculations on some free website. The type of test affects the calculation. So it's important that you know which type test you have. We have, by looking at the symbol, whether you have not equals, greater than, or less than in the alternative hypothesis, that's going to determine the type test. We have what's called a one-tailed test if the alternative hypothesis contains less than or greater than. And I'm going to show you why in just a minute. It's called a two-tailed test if the alternative hypothesis contains not equal. Because the idea of not equal implies that it could be less or it could be more. Make that a little bit better. All of the tests are based on a distribution. Primarily, the one we focus on most of the time is the normal distribution. So if we're thinking about when our our alternative hypothesis, has the mean is less than some number, which means our null would have to be the mean is greater than or equal to some number, and you're thinking about the distribution. If we're saying that our variable is less than a number, then let me label this correctly, sorry. Okay, remember with our normal distribution, we would have our mean in the middle, and we're trying to claim, or we believe it is less than that. So less than, we would have this area or this region on the left, and the only option is to be less than. And so because it is less than, we only have this one option. That's why it's called a one tail. More specifically, sometimes you'll see this one called a left tail, because less than, your region is on the left side. If we had the scenario where we have the mean is less than or equal to a number so that our alternative hypothesis is greater than a number. Again, if we're thinking about our normal bell-shaped distribution with the mean in the middle, and we're trying to claim that we're greater than would be some region to the right. But again, you only have that one option because the only option is it could be greater. So this one is also a one-tailed test because you only have one region. It's also specifically called a right tail because the region is on the right. Different researchers are going to use different terminology, so I'm trying to make sure you're familiar with the various terminologies. The third option is that you have the mean is equal to a number for the null, excuse me, and then the alternative is the mean is not equal to a number. Well, when we say something is not equal, it's not the same. That means it could be less or it could be more. I don't know. We're just saying that it's not the same. And so I have to allow for the possibility that it could be less. So we would have a region on the left, or I have to allow for the fact that it could be more. So in this case, I have two options because I don't know. I just know it's not the same, that it's different. This is the two-tailed test. And again, it's important that you're able to identify whether you have a one-tail or a two-tail because that affects the calculations of your test statistic. And again, we make that determination by looking at the symbol in the alternative hypothesis. And I think it'll make more sense as we get into examples, but we got to get through the steps first. So after you have posed your question, proposed your answer so that you're able to state both the null and the alternative hypothesis, in the second step of the process, if you were doing this in reality, you would actually go out at that point and collect your sample. You would collect the data and come back and do the descriptive statistics that we've been learning about: the mean, the median, the mode, the range, quartiles, all that kind of stuff. Well, I don't have time for you to go running about collecting data. So for us, you will simply identify the given information that's in the scenario. Now, the information that you need, it depends on, and I don't know why I have this here, it depends on which test is going to be conducted. Okay, I don't know why I've got two blanks there. Okay, it depends upon what type of data you're going to deal with. It depends on what type of information you've been given as to what information you're going to need. And that really is the third step. Once you identify, really this is probably, once you identify the information that you've been given, then that can help you determine which test to conduct. And again, we're going to be looking at a variety of tests. So step 3 is to determine which test to conduct. And again, I have listed here the ones that we're going to focus on, and there are at least 9 of them. These, just for so you'll know, because we're going to talk about this later, these are the parametric test. There's a whole different list for non-parametric. Some of these you learned about in Stat 1401 or Elementary Statistics 1. Others of these will be new. So I want to kind of give you an overview of some of them, and then as we get to the others, we'll come back and think about what type of information we have. So the first one that we're going to talk about is the one mean z-test. With the one mean z-test, you have quantitative data. Okay, so we would have numbers. Remember, quantitative data is numbers. Our n, which is our sample size, is greater than or equal to 30. It's what we would consider a large sample. The population standard deviation is given or known. And for us, that's going to be the determining factor. If you know the population standard deviation, that is going to be the big red flag waving in your face saying, do a one mean z-test. Again, there are other considerations that if we were doing this in reality that we might take into consideration. But for us, that's going to be the determining factor. The one mean z-test is related to our normal distribution that we've been talking about. Remember, with our normal distribution, we have that nice bell-shaped continuous curve that is symmetric about its mean. In order to conduct a one mean z-test, you need the population mean, which is the Greek symbol mu. You need the population standard deviation, which is the Greek letter sigma. You need the sample mean, which is x bar. You need the sample size, which is n. And you need something called the level of significance, which is alpha. And I'll talk about level of significance in just a minute. I'll have to go off to the side and do that. The second test that we're going to talk about is a one mean t-test. It is also used whenever you have quantitative data. So again, you'll have numbers. Your sample size is less than 30, so you have what is considered a small sample. The population standard deviation is not known or given, and it's related to the student's t distribution, which we talked about with confidence intervals. Remember, the t distribution is very similar to the normal distribution. It's still that bell-shaped, smooth, symmetric curve, and it's symmetric about the mean. But the difference is it doesn't taper off as fast, so you have more area in the tails. Again, notice here that it says the population standard deviation is not given or known. What you do know is the sample standard deviation. And so again, that's kind of our clue that we're going to use a t-test. Again, for our purposes, if you do not know the population standard deviation, we will use a t-test. The statistics that you need for doing a one mean t-test is, again, the population mean, which is mu. You'll have the sample standard deviation, which is S. You still need the sample mean, which is X bar. You still need the sample size, which is N. And you still need the level of significance, which is represented by the Greek letter alpha. Those two, the one mean Z and the one mean T, we do talk about in Elementary Statistics 1 in Stat 1401. Some of the ones that we do not talk about in the first course that we're going to look at in this course are the one mean independent two mean independent t-test, the two mean dependent or paired t-test, a one proportion z-test, as well as a two proportion t-test. Now, all of those, just as a side note, do relate to quantitative data. Okay, so again, for all of these, we will have numbers. And we'll talk more about what statistics or what information is needed when we get to those problems and how do we know that we should use one of those tests. The two mean are in Module 3, and as noted, the proportions are in Module 4. We will also talk about in Module 3 the one-way analysis of variance, which is also called ANOVA. It's abbreviated ANOVA. It's actually kind of a combination deal because it is quantitative data. It's numbers sorted by a qualitative variable. So we take our numbers and we sort them into categories. Maybe we look at GPAs by the campus location at Georgia Highlands, or we look at the age based on the county of residence. Again, you're sorting numbers into categories based on the qualitative variable. The other thing with ANOVA, just as a side note, you have to have at least 3 categories. If you only have 2, then you're going to do a two mean independent t or a two mean dependent t. So ANOVA gets us into what if we have 3 or 4 or 5 or 10? That's when we get to ANOVA. We will also talk about correlation. Correlation deals with what we call bivariate quantitative data. Bivariate, bi meaning two, so two variables. So correlation, we usually have two variables, both of which are numbers, because remember, quantitative data is numbers. So usually with correlation, we're looking at two numbers in relationship to each other. And then one of the last ones that we talk about is chi-square. And chi-square is one of the few analyses we can use for qualitative data. Okay, it deals with what if you have words or categories or phrases. There are actually three different chi-square tests. There's one called goodness of fit, test of independence, and test of homogeneity. And that'll be our focus in Module 4. So again, there's at least 9 different tests that we're going to talk about. And again, these are the parametric tests. In some cases, there is a similar non-parametric test. And we'll talk about that a little bit later, what are non-parametric tests. Okay, before I move on, well, let me get to the next step, and then we're going to talk about the level of significance. Okay, so we have to figure out which test do we need to do. And again, the test that you're going to do depends upon what information you have and how much information you have. Once you've identified which test you're going to conduct, then we're going to use Minitab, and we're going to calculate and record. Guys, record means to write it down. Okay? You can't just copy and paste or whatever. You have to record it. You got to write it down. You write down the test statistic and the corresponding p-value. If you're thinking about this in terms of a court case, this step where you are calculating and recording the test statistic, this is your evidence. Okay? This is like the evidence that's being presented in the court case. Let's talk about a p-value for just a minute, and then I want to talk about level of significance. Okay? A p-value is a probability value. If it is a probability, remember we learned early on with probability that probabilities are between 0 and 1. It could be 0. Remember, 0 means no way, no how is it happening. The event is impossible. It could also be equal to 1. 1 means it's definitely happening. It's a certain event. But then we can have any decimal value, fraction, or whatever in between 0 and 1. So the p-value represents a probability, and its value will always be between 0 and 1, meaning it'll never be negative, and it should never, ever be greater than 1. What the p-value represents, the p-value is the probability of getting the same test statistic over and over and over again if our null hypothesis is true. Remember, we're making the assumption that the null hypothesis is true unless the evidence proves otherwise. And so the p-value is the probability that we would get a similar test statistic with multiple or different samples. And I've got that written out here. It says results from another random sample will be as extreme or more extreme than the results of the given sample. Again, assuming the null hypothesis is true. Okay, I want to talk for a minute about the level of significance. And I'm going to go back over to where I had our kind of plans for today to talk about level of significance. Prior to the midterm, or just before the midterm, we talked about the confidence level. And you were asked to find the confidence interval. Remember, the confidence level was the probability that you were correct, that your population parameter fell within that particular interval. So the confidence level is the probability that you were correct. Normally, remember, it was stated as a percentage. The more common ones were 90%, 95%, and 99%. And I believe we talked about it, but it's been a while since we've had spring break in here, that if there is the probability you're correct, there also has to be the probability that you're wrong. The probability that you're wrong is called the significance level, or the level of significance. And it's represented by the Greek letter alpha. The two together, remember, have to total to 100%. So if my confidence is 90%, my significance level would be 10%, as a decimal is 0.10. If my confidence level is 95%, my significance level is 5%, which would be 0.05. If my confidence is 99%, the significance level is 1%, or 0.01. Okay, so that's kind of the idea of the significance level. We talk about confidence intervals, and we look at it kind of from that positive perspective, probability that I'm right. When we get to hypothesis testing, we're looking at the probability that we're wrong, because we're assuming the null is true, which is, we kind of want it to be true. And so we're looking at the probability that we're wrong. And that's called the significance level. And again, you want that value to be low. Again, 1%, 5%, or 10%. So I believe we talked about that before, but I wanted to remind you about it. Okay, so after we have gathered our evidence and it's presented, then we have to make a decision. It's kind of like, again, thinking about the jury trial, we assume that the defendant is innocent until proven guilty. The prosecutor presents their evidence. The defense presents their evidence. And then the jury goes out to deliberate and to make a decision that they're then going to report back to the judge or to the court. And so it's the same idea with hypothesis testing. We have proposed our answer, our hypothesis. We gather the data and the evidence, and then based on that evidence, we're going to make a decision. There are two decisions. These are the only two options you have. You either are going to reject the null hypothesis, or you're going to fail to reject the null hypothesis. And we make that decision by comparing the p-value to the level of significance. Remember, the p-value is the probability that we would get that same test statistic over and over again. We would get the same results with different juries. And we compare that to the level of significance, which is the probability that we're wrong. The guidelines for making that decision are very specific. They do not change. Regardless of what test statistic we're calculating, what evidence we're presenting, these guidelines do not change. If the p-value is less than or equal to the level of significance, then you reject the null hypothesis. In symbols, we write if p is less than or equal to alpha, we reject the null. If the p-value is greater than the level of significance, then you fail to reject the null hypothesis. In symbols, we write if p is greater than alpha, we fail to reject the null. Now, let me pause here for a minute because I want to talk about those phrases. Guys, it's reject the null and fail to reject the null. Never, ever should you say that you accept the null hypothesis. That is a huge no, no, no in statistics. Again, think about it from the perspective of a court case. When the jury returns to the courtroom, they're either going to say the defendant is guilty or not guilty. A jury never concludes that the defendant is innocent. They're either guilty or not guilty. Guilty implies there was enough evidence to convince the jurors that the defendant did the crime. Not guilty means there was not enough evidence. They were not convinced based on the evidence presented that the person did the crime. Because they could get it wrong. The person really could have done the crime, but the evidence did not convince them. So we don't come back and say guilty or innocent. It's guilty or not guilty. It's the same idea with hypothesis testing. We're either going to reject the null because the evidence convinced us that it was wrong, or we're going to fail to reject the null because the evidence did not convince us that it was wrong. But if I had more evidence or different evidence, we could get a different conclusion. Never, ever say that you accept the null hypothesis. Your options are to reject or fail to reject. After you've made the decision, and I don't know if you've ever been on a jury, but typically after the jury deliberates, before they go back into the courtroom, there's usually a paper, a document that has to be filled out that indicates what the verdict is. Okay, that's like step 6 of our process. In step 6, we write a final conclusion in terms of the true hypothesis, and you must always include the level of significance. Now, again, those steps, I think, will become clearer and more understandable as we get into some examples. And I hope we're able to do that a little bit later today. But before we move on, do you have questions about this process? Again, you haven't seen it in action yet, but do you have questions that I can try to address before we do move on and begin using it?
So the only options that we have is it's only reject or fail to reject it. Is that
Yes,
correct?
yes, ma'am. Those are your only 2 options.
Okay, just double checking. And
Uh,
we're also going to see the examples.
Yes, I don't, we may not get to the ones at the end of this document today, Nana, but we will come back and do them. If not today, we will look at them on Wednesday.
Okay, thank you.
You're welcome. Other questions? Okay, before we dive into the examples, I want to talk about this idea between parametric and non-parametric test, because we're going to kind of be talking about those, going back and forth between those 2 type tests. And so I want you to understand the differences. Okay, so I'm going over to the PowerPoint that I have, and it should be available to you in the course on parametric and non-parametric. And just so you're aware, it does indicate here on this PowerPoint that a lot of this information was taken from this particular website. Okay, it's not actually part of your text. Okay, so let's talk about parametric and non-parametric test. Oh, it's going to lock up on me. Hold on just a second. I have to stop the share, and then I have to tell it to share again. Okay. Okay, so, oh, come on. Why are you doing that? It's wanting to be difficult this morning. Okay, so we're going to compare non-parametric, and I'm going to give up because it's not going to do it the way I want it to. We'll do it this way. Okay, parametric versus non-parametric. It's not cooperating, so I'm going to do it this way. Okay, so parametric is used with quantitative data. Okay, it can be used with any quantitative data, but the big deal with using a parametric test is that we assume we have a normal distribution, that our variable is normally distributed. We also assume we have no outliers within the data set. We also assume we have equal variances or equal standard deviations. And guys, those are some pretty big assumptions. We're going to learn in just a few minutes there is a way to determine whether a variable is normally distributed or not. But assuming that we have no outliers and equal variances or equal standard deviations, those are some pretty big assumptions. If our data set is large enough, then we don't really have to worry about those things. But if we're dealing with a small data set, we may have to be concerned. A parametric test looks at the relationship between the means. It's a test. It tests group means, the averages. Again, as I pointed out, a large sample is best. And a parametric test has what is termed more statistical power. The idea of power is that the test is more likely to detect differences when they truly exist. It's like it's more accurate. That's what they call the power within statistics. And so a parametric test has more statistical power. It tends to be more accurate, more on target than a non-parametric test. But again, you have to realize with that parametric test, we've made those big assumptions that we have a normal distribution, that we have equal variances, and that we don't have any outliers. So if you have a scenario where you know the distribution is not normal, or you have outliers within the data set, then you may want to consider using what is called a non-parametric test. Non-parametric test can actually be used with quantitative data, but it can also be used with qualitative data. So that's one of the usefulnesses. That's a weird way to say it, but one of the things that's useful about non-parametric test is it can be used with qualitative data. With non-parametric, we don't have to assume a normal distribution. In fact, sometimes these tests are called distribution-free tests because we don't rely on any particular distribution. We don't have to know that it's normal. We don't have to know that it's, say, exponential or binomial or anything. We could have a completely unknown distribution and still be able to do a non-parametric test. The non-parametric test does allow for outliers. We can have variances or standard deviations that are not equal or that we don't even know. The difference is for a non-parametric test, we look at the medians as opposed to the means. Parametric, we look at the means. Non-parametric, we look at the medians. We can also use a non-parametric test if we have a small sample. The downside is it doesn't have as much statistical power. A non-parametric test is not as accurate as a parametric. So if we can use parametric, that's what we prefer to do. But if it's not possible, then we can still do an analysis. It's just that the analysis perhaps is not as accurate or as, quote, powerful as the parametric. So again, you have to think about which test should you choose. Should you do parametric or should you do non-parametric? Again, if you have the option to do parametric, that's what you want to do. But again, it's usually quantitative data. The mean accurately represents the center. Remember, mean is a measure of center. So the mean accurately represents the center of the data, which implies we have no outliers. And typically we're going to have a large sample because once we get to a large sample of 30 or more, we can assume we have a normal distribution, or we can apply the central limit theorem. For non-parametric, you could have quantitative data, usually data that's at the nominal or the ordinal level, or you could have qualitative data. The median more accurately represents the measure of center, which typically implies you have outliers and you have a small sample, or you don't know the distribution, or you know that it's not normal. Now, I'm going to give you, as we go throughout these lessons, I'm going to give you very specific guidelines on when to do parametric and when to do non-parametric. Again, that's for the purposes of this course. If you were doing this, real research, real world, then you would want to go through and kind of do this checklist of which one of these tests would be better to use. So we're going to learn about, in modules 3 and 4, we're going to learn about the two-sample independent t-test, which has its comparable non-parametric test is Mann-Whitney. We're going to do the two-sample paired t-test. Its comparable non-parametric is Wilcoxon. For one-way analysis of variance, we have Kruskal-Wallis. And then for the Pearson correlation coefficient, we'll talk about the non-parametric test, Spearman-Rank. So we're going to kind of be toggling between parametric and non-parametric throughout Module 3 and Module 4. We're also going to include 2 post hoc tests. Post hoc test takes us basically one step further. Once we've kind of come to our conclusion, we go one step further. Maybe think about it like the sentencing phase of a trial. Okay, once you've, presented the verdict, then the defendant may be sentenced or not. And so we go one step further. It's called a post hoc test. And the 2 post hoc tests that we're going to talk about are Tukey's test and Cohen's D. Cohen's D, if I remember correctly, goes with the two-sample t-test, and Tukey's goes with ANOVA. Okay, so it just takes us one step further and gives us a little bit more information. Now, again, for your purposes, I'm going to give you very specific guidelines on when to do the parametric and when to do the non-parametric. Okay, but hopefully the primary differences are that for the parametric, we test the means. For the non-parametric, we do the medians. Questions? Guys, did y'all let me go through that whole thing without sharing? Okay, there is a PowerPoint here, guys. I do apologize. It looks like I forgot to share my screen. But it is available in D2L. So I kind of toggled through it there.
I think you tried to open it up, but
okay.
It didn't work.
Y'all stop me, interrupt me, let me know. Okay, I'm not immune to making a mistake. Okay, so I want to move on then to the idea of normality. Okay, because again, remember, for a parametric test, our assumption is that we have our variable is normally distributed. Now, a lot of times in the scenarios that we're dealing with, we're told that. But guys, in the real world, if you were doing real data that you had collected for yourself, you wouldn't necessarily know if it was normally distributed. So kind of the first hypothesis test, if you will, that we're going to focus on is the test of normality. Okay, is the test for normality. So that's the one we're going to start with. Are there any other questions? And I think I've got the share on now, so. Okay, so what are normality tests? It's actually a test, not plural. The normality test is used to determine whether the sample data has been drawn or collected from a normally distributed population with some tolerance. Now, the idea of tolerance is, there's an allowance for you could be off or could be you could be off a little bit. Okay, but the normality test is going to determine whether your sample data, for your variable, has been drawn from a normally distributed population, which allows us then to make the assumption that we have a normal distribution. Again, we talked about there are a lot of our statistical tests that assume we have a normal distribution. It's called a parametric test. So if we're going to run things like a one mean t-test or a two mean t-test or the one-way or even two-way analysis of variance, we are assuming we have a normal distribution. And again, if I'm not told that in the scenario, I really should run the normality test first to ensure that my variable is normal. Now, we kind of don't, we do that. There are about, I think, 3 different normality tests. We're only going to discuss one of those, and the one that we're going to discuss is called Anderson-Darling. Okay. Minitab will give us a graph and conduct the test for normality for us, but the one we're going to use is called Anderson-Darling. And again, what we're doing is we're basically asking ourselves, is this variable normally distributed? And ultimately, it's going to be yes, it is, or no, it's not. Okay, so the Anderson-Darling test is a statistical test of whether or not a data set comes from a certain probability distribution. Again, we're asking, does it specifically come from a normal distribution? The most common use for Anderson-Darling is to determine whether it comes from a normal distribution or not. Remember, the normal distribution is our nice bell-shaped curve with the mean in the middle. Okay, so in terms of, remember, we have to state our hypotheses. That's the first step in a hypothesis test. For the null hypothesis, there's a very specific way to state it for the test for normality. The null hypothesis will state that the sample or the variable follow a normal distribution. Okay, so we would say the variable, whatever the variable is, and we'll write this out in a few minutes, follow a normal distribution. So our question, to kind of help you put this in perspective, our question is, does the variable, or I guess we could say, is the variable normally distributed? Does the variable follow a normal distribution? Or you could say, is the variable normally distributed? Okay, so our null hypothesis, remember, the null hypothesis must always contain equal. And so this phrasing that we follow a normal distribution, that's the idea that it's equal or the same as a normal distribution. The alternative hypothesis, remember, has to be the exact opposite. So mathematically, it would have to say it's not equal or it does not follow a normal distribution. Again, so it's kind of like, again, you have your yes. The null is like saying, yes, it does follow a normal distribution. The null, or excuse me, the alternative is like saying no. And those are your two choices. It either follows it or it doesn't follow it. It is normally distributed or it's not. The phrasing of the conclusion is very specific as well. The intermediate steps of getting your data and all that are going to be the same as well. But our null hypothesis will always be that it follows a normal distribution. The alternative will be it does not follow. The conclusion is we say preliminary analyses showed the data set for the variable is or is not normally distributed as assessed by Anderson-Darling, and you put in the value with a p-value of such and such. Okay, and as we go through the examples, I'm going to model this for you. Okay, so the first hypothesis test that we're going to focus on is the test for normality using Anderson-Darling. And then I have, these are the keystrokes, and let me tell you what slide this is. On slide 5 of this PowerPoint are the keystrokes for Minitab. On slide 5 of the normality test PowerPoint are the keystrokes for Minitab. Okay, and then we have a couple of examples. So I've copied those over to my paper, to our outline for today. Okay, so the first, I'm going to make us a note here. The first type of hypothesis test that we're going to do is we're talking about the test for normality. Hypothesis test. Okay, so I want to try to go through those steps that we outlined earlier as we go through this question. Okay, so here's the first example from the PowerPoint. I've pulled it over to my paper. And it reads, the Institutional Effectiveness and Strategic Initiatives Department at Georgia Highlands College wants to know if the ages of students in fall semester 2022 are normally distributed. A sample of all students in two different Stat 1401 classes at GHC are surveyed and the results are provided. Now, I gave you, if you look at this lesson in Module 3, this is the lesson on hypotheses, p-values, and normality. Okay. If you scroll down, I have the data set for the normality test, example 1, example 2. So these are here in D2L. Okay, so the first step in any hypothesis test is to state the hypotheses. Typically, you'll see them written. The null hypothesis is written on the top, and the alternative is written on the bottom. They're usually stacked, one on top of each other. The null is always on the top, and the alternative is always on the bottom, and they are clearly labeled using the symbols H sub O, and I'll make a little note out here to the side to help you remember that that's the null. This is the null. The null must always contain equal in some form. H sub A is the alternative, and it cannot contain equal. The question here is we want to know if the ages of students in fall semester are normally distributed. So that is my clue, because it's asking me, are they normally distributed? That is my clue that I'm going to do the test for normality. For the test for normality, my hypotheses are pretty much predetermined for me. The null hypothesis will be the ages of students in fall semester 2022 follow a normal distribution. That's what you would write. Notice we're writing it out in words. Again, the idea that it follows implies that it's equal or the same as a normal distribution. The alternative would be the ages of students in fall semester 2022 do not follow a normal distribution. Okay. Step 2 is, I usually say, is we identify the players. You have to identify the information that you need to work that problem. Well, in order to make this determination for the whether or not the data is normally distributed, you need the raw data. Okay, so we need the raw data. In this case, we need the ages of students in fall semester 2022. And again, I've given you that in D2L. Now, the other thing that we need when we are making our decision or working a hypothesis test is the level of significance. Which again is represented by alpha. Oftentimes it is stated in the problem. But if I go back up here and look at this paragraph, it doesn't indicate, it doesn't say use the level of significance of blah, blah. It doesn't talk about it. Guys, if it's not stated, okay, the default, if it's not stated, is always and forever 0.05 or 5%. if you don't know, sometimes researchers will leave it open-ended so that the reader can use whatever level of significance they want, whether they use the 5%, the 1%, or 10%. The most popular or the most used level of significance is 0.05 or 5%. So if it's not stated, we will default it to 0.05. Okay, so I have those two things now. I have the raw data. Step 3 is to calculate and record the test statistic, which in this case is going to be the Anderson-Darling, and its corresponding p-value. Remember, the p-value is a probability value. It's a probability you would get those same results over and over and over and over again. And it is unique to each test statistic. The p-value is unique to the test statistic. Okay. To do this calculation, we use app.minitab.com. The keystrokes were on slide 5 of the PowerPoint. But before I can do anything, I've got to get my data into Minitab. Okay, so let me get Minitab opened up. I had it opened earlier, but I bet it's gone to sleep. Okay, so I gave you the data in the course, and I've already downloaded it this morning. It is the class survey results fall 22 with AGPA. I checked it this morning and downloaded it. Okay, now I really only need the column for age, but I'm going to copy the entire spreadsheet. Okay, remember, click in the corner, we copy, and then we paste. Okay, so I'm focused on age. I want to know, is age of GHC students in fall 22 normally distributed? I've gotten the data. Now I'm going to do the keystrokes that are on slide 5. I go to the top of the screen to Stat, Basic Statistics. I'm going to have to scroll down to Normality Test. Okay, it's near the bottom. Oh. Okay, so Stat, Basic Statistics, and then I got to scroll down to Normality Test. I have to tell it what variable I'm interested in. We're interested in age. We do not want percentile lines, and we are using the Anderson-Darling. There are 2 others, but we're only going to do Anderson-Darling. Okay, so we choose the variable, no percentile lines, and we're doing Anderson-Darling. I'm going to click OK. And what appears on the screen is this graph. Okay, and I'm going to copy it over to my paper so you guys can see it. Okay, so it gives me this line, this red line, is where I would want my data to be kind of clustered or clumped if it is normally distributed. Off to the side here, it gives you the mean of the data, the standard deviation, the sample size. What you need is AD and the p-value. AD stands for Anderson-Darling. So my Anderson-Darling was 7.020. So I'm going to write it down. Okay. So my Anderson-Darling is 7.020. And then it tells me that my p-value, it actually says it's less than. We're just going to say that it's equal to 0.005. Okay, and I get those two numbers from the right-hand side of my probability plot. Okay, so that is step 3. I have my Anderson-Darling and I have my p-value, and I've written them down. So there's the evidence. Remember, that's the evidence. Then I go to step 4. Step 4 in the hypothesis testing process is to make a decision. And remember, you only have 2 options. You're either going to reject the null or you're going to fail to reject the null. And to make that decision, to make that decision, you compare the p-value to the alpha. So if p is less than or equal to alpha, you reject the null. If p is greater than alpha, you fail to reject. The p-value we just calculated in Minitab. The alpha is your level of significance. That usually is given in the problem. So in this scenario, my p-value was 0.005. My alpha is 0.05. Now, from my years of experience, one of the biggest issues that students have is comparing these decimals. What I recommend is that you compare it digit to digit. If we look at the first digit after the decimal point, for the p-value, it is 0. For the alpha, it is 0. They're the same. If I move to the second digit for the p-value is 0. For the level of significance, it's 5. 0 is less than 5. So the p-value is less than or equal to alpha. If the p-value is less than or equal to alpha, we are going to reject the null. Guys, that is your decision. Again, you have to write that decision down. So my decision, because p is less than or equal to alpha, my decision is to reject the null. If I reject the null, what that means is that my null hypothesis is wrong. If the null hypothesis is wrong, then by default, the alternative hypothesis is true or correct. So I'm going to go back up here. We decided we were going to reject the null. If we reject the null, that means the null is false. And by default, then the alternative is true. So if the alternative is true, our conclusion is that the variable, the ages, do not follow a normal distribution. So my last step in the hypothesis testing process is to write my conclusion. Now, for the test for normality, again, that conclusion has very specific wording. We say preliminary analysis of the ages of students in fall 2022 is not normally distributed. I think I left out a word. Hold on just a second, guys. I think I left out a word. Showed that. Okay, I did leave out a word. I'm sorry. Sorry about that. Preliminary analysis showed that the ages of students in fall 2022 is not normally distributed as assessed by Anderson-Darling equals 7.020 with a p equal to 0.005. So we concluded that the ages are not normally distributed, which would then mean if I were going to conduct some kind of a different hypothesis test, I would likely use a non-parametric test because my variable is not normally distributed. Everybody okay?
Yes.
All right, so let's look at the second example. The second example says a local bank manager wants to know if the ages of loan applicants is normally distributed. Now, guys, this doesn't always have to deal with ages. It just so happens that the two examples I pulled deal with ages, but it doesn't always have to be about ages. We could talk about is the GPAs normal, are the GPAs normally distributed? Or let's see, what else did we have on that data set that might be appropriate? We could say, are the credit hours normally distributed? Are the hours employed normally distributed? Is the number of siblings normally distributed? I can do any variable, but it is a quantitative variable. Okay. All right, so again, this question, they're really asking if the ages of loan applicants is normally distributed. So that phrase is what triggers in my mind that I need to do a test for normality. So the first step in any hypothesis test is to state the hypotheses. Okay, so I would have my null hypothesis and my alternative hypothesis. For, again, it's very lockstep. I would say the ages of loan applicants follow a normal distribution. The null hypothesis will always be that the variable follow a normal distribution. The alternative would be the ages of loan applicants follow, or excuse me, do not follow. Getting ahead of myself. Do not follow a normal distribution. Step 2 is to identify the players. Now again, for the test for normality, you need the raw data for the variable, okay, which in this case would be the ages of loan applicants. And that's given in D2L. Again, this scenario does not indicate a specific level of significance, so we default it to 0.05 because that's the other piece of information we need. Third step in the process is to calculate and record the test statistic, which will be Anderson-Darling, and its p-value. Now again, before I can do anything in Minitab, I got to get the data set in there. Okay. And again, I pulled it down this morning. So I got to pull in it was loan applicants. Okay. So I'm doing age of the loan applicants. So again, going through the process, stat, basic statistics, normality test is near the bottom. I'm doing age, no percentile lines, and we're doing Anderson-Darling. I click OK. And again, my probability plot appears. Let me copy it over here to my paper. No. Hey, notice how on this one you've got that red line and the dots appear to be a little bit more clustered around it than the previous one. But again, over here to the right, you have your Anderson-Darling and your p-value. Okay, so my Anderson-Darling, I'm going to record it. My Anderson-Darling was 0.659. The p-value is 0.077. Okay, I pull those directly off of my probability plot from Minitab. Okay, then we're going to make a decision. We always make a decision by comparing p and alpha. Again, my p-value comes from Minitab. Okay, so I have my p-value. Notice I always list it first on the left-hand side. It is 0.077. My alpha is my level of significance, which was 0.05. Again, I compare it digit for digit. The first number after the decimal for the p-value is 0, for alpha is 0. Looking at the second digit, for the p-value, it's a 7. For alpha, it's a 5. 7 is greater than 5, so p is greater than alpha. If p is greater than alpha, we fail to reject the null. That is the decision. You have to write that phrase. But now what does that mean? If I fail to reject the null, that means the null is true or correct based on the evidence we have, and the alternative is wrong. So again, I'm going back up here to kind of make a note next to the hypotheses. In this case, we fail to reject the null, which means the null is true and the alternative is false. So based on the evidence that we have in this case, the ages of the loan applicants does follow a normal distribution. So then we would write our final conclusion. Guys, don't try to get fancy with the phrasing. I've given you the exact phrasing for the conclusion. Preliminary analyses showed that the ages of loan applicants are normally distributed as assessed by Anderson-Darling equals 0.6, is it 659? Yeah. 659 with a p of 0.077. Again, don't get fancy. Write it exactly as I have told you to write it. Questions? Okay, hold on just a second because I want to show you something. Zoom the recording. And I want us, we have about a little more than 30 minutes left. Do you have questions about normality? Okay, I want to go back then to the examples on the fill in the blank notes and begin to talk about the one mean Z test. Okay, the one mean Z test. So we're going to switch gears now. We're still talking about hypothesis testing, but we're going to focus on, for the next few minutes, one mean Z test. Again, for our purposes, we're going to use the one mean Z test whenever we know the population standard deviation. Okay, that will be if you know the population standard deviation, that's going to be your clue that we're going to do a one mean Z test. Okay, now I would say that this process is the same steps: state the hypotheses, identify the players, calculate the test statistic, make a decision, and write your conclusion. But it's, in some ways, the steps are a little bit more involved, if you will. Okay. It just, for some reasons, it just seems more complicated to students than the test for normality. Okay. Because it's not as specific in terms of stating your hypotheses. Okay. So let's read through this question. It says, a manufacturer of chocolate chips would like to know if its bag filling machine works correctly at the 438 gram setting. It is believed that the machine is underfilling the bags, thus cheating customers. 37 bags were sampled and found to have a mean of 438 grams. Assume the population standard deviation of 14. Using a 0.05 significance level, determine if the bag filling machine is underfilling the bags, which means it's putting less than 438 grams. Okay, so you've got a lot of words here. Okay, couple of things that I want you to notice. Okay, couple of things that's going to help you out. First of all, it's talking about it said I see the word mean. Okay, so that's important to me. It also tells me to assume the population standard deviation of 14. Okay, those two things help me to recognize that I need to do a one mean Z test. And I'm pointing that out because later we're going to be talking about one proportion Z test in Module 4. So when I'm reading this scenario, it's talking about the mean. So that lets me know it's a one mean test. It's only talking about one thing. It's only talking about the bags being filled with chocolate chips. So I'm only talking about one thing. It's talking about mean, has the word mean in the story. And I know to use Z because I know the population standard deviation. Okay, because guys, here's what's going to happen. On the final, I may give you this scenario, and you will have to identify through those clues that this is a one mean Z test. And by the time you get to the final, remember, you're going to have at least 9 different tests. So I'm trying to give you some clues on how to know which test to do when. Okay. So my first step for any hypothesis test is to state the hypotheses. Now, before, when we were looking at the normality test, the hypotheses were pretty much predetermined for you. It would always be the variable follows a normal distribution, and the alternative would be the variable does not follow a normal distribution. It's not so clear cut in these problems. So you have to identify what that hypothesis is. And so when you're looking at these problems and reading this scenario, you want to look for words like claim, believe, think, conclude. Sometimes they even use the phrase want to know. Now, one of the things that I try to do to help students is, if I'm writing these scenarios, I try to put my hypothesis near the end of the problem, kind of in a question form. So if you look at this problem and you look at the last sentence, it says using a 0.05 significance level, determine if the bag filling machine is underfilling the bags. And then they define what underfilling means. That means they're putting less than 438 grams. So that statement that I've kind of squared off is my hypothesis. They actually stated it earlier too in the second sentence, because it says it is believed that the machine is underfilling the bags, thus cheating customers. Guys, this is a prime example of a kind of a real world problem, because in quality control, you have to make sure the machine is putting the right amount in the bag or the right amount in the bottles. Because if you're not, again, you're cheating customers, which could ultimately get you in trouble. Okay. So you want to make sure the machines are working properly. Okay, so you have the hypothesis. We've identified it, but then I've got to decide, is that statement going to be the null or the alternative? So, and it really is totally going to depend upon the words. It says, we want to know if the machine is underfilling the bags, and they define for us that underfilling means it's putting less than 438 grams. So when I see that phrase, less than, hopefully what comes to mind is this math symbol, the less than symbol, which does not in any shape, form, or fashion contain equal. It's just less than. So this statement that we're looking at is actually our alternative hypothesis. Okay, I told you that one of them would be given in the problem. The one that's given in this particular scenario is the alternative. So I've set up my null hypothesis and my alternative hypothesis. H sub O is the null, H sub A is the alternative, and I'm going to translate this into symbols. For a one mean z-test, we write it in mathematical symbols. We're saying that the mean is less than 438 grams. Guys, remember that the hypothesis is a claim about the population parameter. Our parameter in this problem is the mean, and the symbol for the population mean is that funky looking U symbol, the Greek letter mu. Now I'm going to indicate this is the one that's given. You don't have to, but I'm trying to help you realize where it came from. So the statement in the problem is that the mean is less than 438 grams. I know that the null and the alternative have to be exact opposites, and that the null must contain equal. So if the alternative is less than, then my null has to be greater than or equal to that same amount of 438 grams. They have to be the exact opposite. And you always pair greater than or equal to with less than. And so since I know the alternative was less than, the null has to be greater than or equal to. Guys, that is probably the hardest part, or one of the hardest steps for students to grasp or to do correctly within hypothesis testing. But if you set your hypothesis up incorrectly at the beginning, it's going to screw everything else up. Okay, so do you see, can you follow the logic and the words that I've highlighted to get to those hypotheses? I'm assuming you're good. Okay, step 2 is to identify the players. Okay, for a one mean z-test, all of the information you need is given in the problem. Okay, so you need, I'm going to write it out, mu, sigma, x bar, n, and alpha. Okay, you need the population mean, that's mu. That is the value that you have in the hypotheses. You need sigma, which is your population standard deviation. You need the sample mean. You need the sample size. And you need the significance level. And guys, all of that information is clearly identified in the story. Okay, so I know that my population mean is 438 grams. I'm scrolling back up to my scenario. In the third sentence, it says 37 bags were sampled and found to have a mean of 435 grams. Assume the population standard deviation of 14, and then using a significance level I don't want that color of 0.05. Guys, everything is there. Okay. It says assume the population standard deviation of 14. It says 37 bags were sampled. The sample mean, let me get the right color, orange. The sample mean, or the mean for those 37 bags, was 435. And my significance level is 0.05. All of those numbers come directly from Minitab. Excuse me, from the story. And they're usually pretty straightforward, so there's not a lot of guesswork. Step 3 is we're going to calculate the test statistic, which in this case is going to be a Z, and its p-value. And to do that, we are going to use Minitab. Now, let me see if I've got the PowerPoint for this lesson and can tell you what slide number it's on. Okay, it is on for the PowerPoint for the 1 mean and 2 mean hypothesis testing. It is on slide 5. Okay, it's on slide 5. Excuse me. Okay, so let me make you a note there. It's on slide 5. Okay, so I'm going over to Minitab. I don't have to have any data because I have all of the summarized data. So we go to Stat, Basic Statistics, 1 sample Z. We have summarized data because we have all of those numbers given to us in the problem. They're summarized. My sample size was 37 bags. My sample mean was 435. The known population standard deviation was 14. We're going to perform a hypothesis test. My hypothesized mean was 438. Okay, so we're entering the information that we pulled out of the problem. This is the important step. Options. My significance level was 0.05. The confidence level then is 95%. Okay, let me go back over here and make a note. Okay, because Minitab wants you to use the confidence level. So if my significance level is 0.05, that means my confidence level is 95%. Remember, they have to total to 100 or 1. And the other piece is I need to know what symbol is in the alternative hypothesis, and it was less than. Okay, so I have a 95% confidence level, And the symbol in my alternative hypothesis is less than. Remember, I told you that symbol in the alternative hypothesis, which determines whether you have a one-tailed test or a two-tailed test, affects the calculations. So you have to choose which symbol you have. And in this case, it was less than. So I click OK. I click OK again. And I get a variety of things. What I need is this information under the header test. Okay, under the header test. And let me scroll back down here where I can insert this. I don't want to be in the footer. I want you to close. Okay, so I'm going to paste in my results. And what I need, okay, I'm looking for my test statistic and its p-value. I need the z-value is my test statistic. That's my z. And then you have the corresponding p-value. So this is your p-value. So I would record that my z is negative 1.30 and my corresponding p-value is 0.096. That comes directly from Minitab.
For the z value, does it have to be a negative?
In this case, yes. Because here's why. Z values can be positive or negative. It's negative because see how this sample mean is smaller than the population mean?
Yes.
And that's indicated by that negative sign. So the negative is important.
Okay.
Okay, so step 4 then is we're going to make a decision. By comparing the p-value and alpha. The p-value, as always, comes from Minitab. So my p-value in this scenario is 0.096. My alpha was given as 0.05. We're going to compare those, again, digit for digit. The first digit after the decimal point for p is 0, for alpha is 0. Then I'm going to do the next one. The second digit is 9 for the p-value and 5 for alpha. 9 is greater than 5, so p is greater than alpha. If p is greater than alpha, we fail to reject the null. If we fail to reject the null, just again to help you remember, that means that the null is true. So again, I'm going back up here. Okay, so we have said we're going to fail to reject the null, which means the null is true and the alternative is false. And guys, in this particular scenario, that's a good thing because we have concluded that the alternative is false or wrong, which means we are not underfilling the bags. See, we've proven the evidence shows that we're putting 438 grams or maybe more in the bags. So the machine is working properly. Now I have to say that. I have to write my conclusion. Okay, so I'm going to say at the 0.05 level of significance, the machine is not underfilling the bags at the 438 gram setting. That's what the evidence is showing us, is that it is not underfilling the bags. Notice that I pretty much took this hypothesis that we identified earlier and I added a word. I added the word not because the evidence showed that we were not underfilling. Now, I've tried to be very deliberate because I know that hypothesis testing is one of those things that students tend to struggle with. Some would tell you it's probably one of the hardest things we do all semester, but it's also what we're going to do the rest of the semester. So it's important that you understand the steps. So what I would tell you to do at this point is to focus on the normality. Okay? Kind of understanding that process. We haven't really gotten far enough into the one mean Z or the one mean T. We'll pick that discussion up on Wednesday. We'll do some more examples with a Z. We'll talk about one mean T, and we're also going to do the two mean test on Wednesday. But the more familiar you are with those steps of stating the hypothesis, identifying the players, calculating the test statistic and its p-value, making a decision, and writing the conclusion, the better off you're going to be. So do you have questions this morning before we adjourn for the day?
In the what's that normality? It has to be only positive, no negative on that.
Anderson-Darling, that statistic will always be positive.
Okay.
With you're going to find with Z as well as with T, it could be negative.
Okay.
And the negative simply implies that your sample data was below what you projected, what you hypothesized. That's all that it means.
That's the given one?
That's the given one. See if you go back to this problem again that we were looking at with the chocolate chips, my my sample, which was 435 grams, was less than what we predicted at 438. So
Yes.
because it was below it, we got a negative value. Had these numbers been reversed, I would have gotten a positive value. But it's important that you get them identified correctly. Make sure, you want to make sure you identify which one is the population and which one is the sample. And you'll often see it. Notice how this was kind of written. It doesn't literally say sample mean, but notice how this said 37 bags were sampled and found. So if you think about the sentence structure within English, the fact that they're initially saying 37 bags were sampled, they're continuing to talk about that sample. That's how I knew this was the sample mean, even though it didn't literally say sample mean. You really have to pay attention to the way things are worded and phrased and kind of the sentence structure to help you make sure you identify things correctly.
Okay.
Other questions?
I don't think I have any more.
Emmanuel, Gabriella, or Disney, do you have any?
No.
No.
All right, then I will, it'll take me a little while, but I'll get this processed and posted up. But I will see you guys on Wednesday.
Okay.
You
See
have
you
a good
on Wednesday.
afternoon.
You too. Bye.
Bye.